Okay, so here's the causal formula we were then deriving. We derived last week. Should probably memorize it. I never have. Like I said, I have the formula and coordinates memorized. But this is that thing where we had 6 formulas that we add up and everything canceled at the end. That's the Lie bracket there. Obviously, you don't need to memorize. I don't really recommend memorizing it. Because, I mean, life is an open book exam, right? Okay, so we have that causal formula. And so now we're off to the races, doing interesting stuff. So today I'm going to teach about the Riemann curvature tensor. We're going to learn all about curvature. So it's going to be pretty exciting. Now I could just write down the formula for the Riemann curvature tensor now, actually. I'll tell you what, I'll do it. I'll impress you. And then I will try to make you less impressed, okay? So this is this sort of like, whoa, where'd that come from, right? Because you're wondering what curvature is, like what's Gauss curvature and generalized and so forth, right? Well, the Riemann curvature is a tensor. And let me just write down the formula for it. First of all, R for Riemann of W, X, Y, Z equals, these are 4 vector fields. Okay? Capital letters for today's lecture will be vector fields. Right, so this is covariant derivative of a vector field in the direction of another vector field. Dot product another vector field. Are you guys handy with the notation yet? The angles, right? I mean, that's the metric, right? I mean, so when you do the angles here, right, with the comma, that's the metric. Not to be confused with the square brackets with the comma. That's, actually, this is their own spot. Okay. When I go like this, that's the metric. When I go like this, that's the Lie bracket. And when I go like this, that's just regular parentheses. Okay. So like, it's just parentheses, all right? Parentheses, did I do it right? Okay. So that's nothing. As is this, right? As is this. These things are just parentheses, right? So there's a comma in the middle, it's Lie bracket, and then so forth. You got it. Okay. So the notation, it's like these notations are all kind of similar, aren't they? Right?
Unless there's something before the square parentheses, in which case it's a directional derivative.
Yeah. Although I mean, technically, I just think of it as parentheses.
Oh,
really.
okay.
It's like whenever you see a vector field followed by a function is a directional derivative, and I tend to put the parentheses in to try to make it easier to understand, right? But sometimes people will write xf is the directional derivative of f in the direction of x. But I like to go like that just to really emphasize.
I see. Okay.
Yeah, because sometimes it's not f, it's f plus g or whatever you know. So. Yeah, you're right. And so I tend to use the square brackets there. So yeah, I tend to use that for a directional derivative. That's arguably notation too. Okay. All right. So what's the let me just impress you real quick. All right. And just write it down. This I have memorized. There you go, that's the Riemann curvature tensor. If you don't mind, I'll put some parentheses in here just to clarify, okay? You don't, normally people don't put the parentheses in, but I think it's helpful. Okay, so let's just go over what this is. You have 4 vector fields, okay? Y is a vector field. Take its covariant derivative in the direction of W. How do you do that? You use that formula. Okay? That gives you a vector field. Now you take the covariant derivative of that vector field in the direction of a vector field. How do you do that? That formula. Okay? And then same thing here. And then there's your Lie bracket. Take the covariant derivative of Y in the direction of that vector field, the Lie bracket. You add and subtract it all up, you dot product with Z, you get a number out each point, otherwise known as a function. Okay? Now, this is the Riemann curvature tensor. This is what curvature is. And so if you're like, gosh, that looks kind of complicated, that's going to be a mess. And welcome to the club. It's a little bit of a mess. Remember that formula for the Gauss curvature in terms of E, F, and G's? Well, in dimension 2, you can rederive that formula from this formula, right? So that's a special case if you're in dimension 2. Now you're saying, well, this is a function of 4 vector fields. Well, you put in E1, E2, E1, E2 for any frame, and then you'll get the Gauss curvature out. Okay, turns out. Okay, so this is connected to that EF and G formula for Gauss curvature. But what I want to do is, I'm giving you an example of a tensor. Okay, because what I want to, when you look at this formula, you're like, okay, that's complicated. Where the hell did that come from? Turns out it's a very natural motivation for it. Very natural. I'm going to try to persuade you. Now I've shown you its complexity. I'm going to try to persuade you today it's actually very natural and the only way it could be. Okay? It's a good goal, right? Most natural thing in the world. By the way, this was the most natural thing in the world. Right? Remember? We wanted it to be torsion-free and metric compatible, and we proved that the connection had to be that. The causal formula is the only one thing it could have been. This is the only thing this could have been too. Okay? But I need to explain this word tensor though. Okay? The word tensor is the operative word. Because if I just say I have a functional on 4 vector fields, that could be, I mean, you realize how complicated, any functional, you put in 4 vector fields, you get a number out? That's ridiculous, right? So in this Riemann curvature tensor right now, it maps, you take any 4 vector fields and you get a number out. But let me tell you about the amazing properties. This is the amazing properties of a tensor in general. Okay? Okay, and by the way, when you learn about tensors, the Riemann curvature tensor, let me tell you my opinion. It's easier to learn the Riemann curvature tensor first and verify it's a tensor, and then you know what a tensor is. Like, don't learn the definition of a tensor first, because it's like, why are we doing this? I don't understand. I'm not motivated. But when I tell you that's curvature, are you motivated now? We're motivated. Okay. So tell me what's so special about this. Something very special. Okay. And so what is a tensor? A tensor means that you're multilinear. Okay. So what it means is that R. So we have 2 properties for each slot. It's just that it's linear in each slot. What does that mean? It means R of, take any function f and multiply it by your W there. That function just factors out. Okay. Now, and then there's a second property of linearity, right? Is that if you take W1 plus W2, by the way, it's 2 vector fields, it's not coordinates or something, okay? One vector field W, the second vector field W, W1, W2. And then you keep the other guys the same. Then you get R of W1, XYZ, so 1. And that's a 2. So that's what, whenever someone says it's linear in the first slot, that's what that means. Okay? And it's not only it has to be linear in the first slot, it has to be linear in all 4 slots. And then also true for okay, so that's and that's what it means to be a tensor. Okay, now do y'all see that restricts functionals on 4 vector fields? There's now, this is like, simplifying things tremendously. In other words, it has the same linearity properties as the metric. right? So just like the dot product, except you're putting 4 vectors in and getting a number out instead of 2 vectors again. So in other words, it has a distributive law. Do you guys get the full power of what we're talking about here? In other words, this is the nicest part. This is the nicest thing we could think of. Like, okay, tell me something nicer than that. Tell me a set of functionals that's better than that, right? Other than just saying they all have to equal 0. You see my point? So it's pretty much the simplest thing. We're looking at the simplest possible functionals on 4 vector fields. That's what a tensor is. Fair? So a tensor, far from being a complicated thing, is in fact the simplest thing. Except that it's a function of 4 vector fields. Other than that, it's like a generalized notion of a dot product. It has a distributive law. Okay? Has a distributive law. Okay? Now you're looking at this formula and you're saying, no, it doesn't. That's obviously not true because I'm going to say the second dot, it's additive on the w's because it's additive here, right? And it's additive here and it's additive there. So the second law, yeah, sure. But in the first law, by the way, if f is a constant like 5, like replace w with 5, the 5 factors out, the 5 factors out, the 5 factors out, right? Everything's fine, right? But that's not a constant f. It's a function. It varies from point to point. That function will factor out here, but how about here? It factors out, and then you got to take the x derivative of it. And so right now you should be thinking, wait a second, that formula, that's not a tensor. That function doesn't factor out, but it does. And I'll tell you why. When you multiply w by f, sure enough, that function factors out here. And then you get an x derivative of f. Now notice that we're not supposed to have any x derivatives of f. There's supposed to be the f. So there are x derivatives of f there. But there are also, when you x derivatives of f in this term as well. And there's a plus sign here, and there's actually a minus sign here and a plus sign there, and they will exactly cancel. So this formula is magic. That's what I'm trying to tell you. Is that in principle it has derivatives of f. In other words, if I take this minus sign and made it a plus sign, it's not a tensor anymore. Or if I take that minus sign and put a 2 there or anything like that, you adjust this any way, shape or form, other than multiply and go by a universal constant. And it will not be a tensor anymore. Right, so that's a magic formula. It's easiest to see that's a tensor in the z slot, right? Because if I take z and multiply it by a function, that function obviously just factors out. Okay, so it's clearly a tensor in the z slot. Showing it's a tensor in the y slot even. Let's say you take y and multiply by a function. Well, here I'm going to get 2 derivatives of that function, right? I got to do the product rule here, and then I got to take a derivative again, right? But then on the other hand, you're going to do 2 derivatives of the function here as well, right? And so you can see there's a plus sign there and a minus sign there. There's a chance things might cancel, right? In fact, let's just look. I won't prove it's a tensor in all slots. I'll do it in the y slot just for fun, okay? And I'll leave it for you guys to play around with the. I already proved it for the 4th slot. Let's do the 3rd slot real quick, okay? And let's just do a back of the envelope thing. Can everyone see this board? You can take it up? Okay. So let's just keep track of derivative terms that come up. Okay, so in other words, if I'm not going to write the whole thing out, it'd take too much time. I want to do this a little bit quicker than that. So what I'm going to do is we're checking the linearity of, I want to look at R of W, X, Fy, Z. And my claim is that this is equal to F, R of W, X, Y, Z, and then plus some additional terms, okay, that cause trouble, okay? Now, when we multiply y by f, okay, we're going to be doing the product rule and stuff, right? And we're clearly going to get 2 derivatives of f here, right? So let me just I'm not even going to show you all the derivative terms. I'll just show you some of the derivative terms. But one of the derivative terms we're going to get is x of w of f. You guys agree that that term's going to come up? Right, because we do the product rule here, and then we take the x derivative of that, right? So that's the second derivative term that's going to come up. Another second derivative term we're going to get that comes up is minus W of x of f. And in both cases, by the way, they're times y, right? So it's going to be all that's times the vector y, which ends up getting dot producted with z. Okay, so. And then, but then look at this term here. We're going to have then plus when we do the product rule, put an fy here, do the product rule, we get the Lie bracket wx, then applied to f. And all that's times y and the dot product with z. But then y'all notice this right here, this is the definition of the Lie bracket, isn't it? That's 0. Y'all see it's second derivatives of f, second derivatives of f. But remember, the difference in second derivatives, that's the Lie bracket. There's your Lie bracket term, this cancels all to 0. Okay? So, and there's two other terms I didn't bother to put in there. And so the point is, this all equals f r of w x y z. Okay? So this actually is a tensor. Now I'm going to actually prove it's a tensor, but I'm going to prove it in a different way. Okay? Now you could go through and check that it's a tensor, and that's a great exercise for you to do. If this was on the exam, which is not. Okay? So we're just having fun here, right? Yeah, go ahead and prove this is a tensor. A personal challenge to yourself, right? You're going to have to understand properties of the Lie bracket, right? And so forth. And so that, there's some good exercises in there. Okay, kind of thinking about things. You'll see this is some good Riemannian geometry calculations. But let me, for now, let me show you, let me not get distracted. That's the forest, that's the trees instead of the forest. I want to show you the forest. Okay, where did this come from? And really, it's the fact that it's a tensor. All right, the fact that this is multilinear, the fact that this actually is linear in each of the 4 slots is the key thing that we want to focus on. And so, for example, let me give you an example of a 1 tensor. Okay? The simplest example of a 1 tensor, what is a 1 tensor? A 1 tensor is something that's eats 1 vector field. So that's a 4 tensor. So I need a, okay, so, well, here's an example of a 1 tensor. You could just take d of a function. Turns out that's a 1 tensor. Why? Because I can put in a vector field x. Let me make sure I follow my notes here. No, okay, I want to put a vector field z. You'll see. It doesn't, none of that really matters, but I just want to follow my notes. Okay, now df, you're like, okay, that's a tensor? Yeah, it's a tensor. Why is it a tensor? Because I'm going to define this just to be z of f, the directional derivative. Okay, so you see how df is a 1 tensor because you put in any vector field and it gives you a number out. Fair enough? And we know it as the directional derivative. Okay, that's a 1 tensor. Is it, by the way, is it linear in each slot? There's only 1 slot. Yeah, it's linear. Okay. All right, now what's a simple example of a 2 tensor? Well, you got the metric, right? Metric is a 2 tensor. So symmetric 2 tensor. But then another thing you could do is you could say, oh, what about the Hessian of the function, which we can write d2f. Okay. And you're like, isn't the Hessian like a matrix? And the answer is, yeah. Remember the Hessian? Take all the possible second partial derivatives. Well, that's when you're on a flat space. Here we want to define, like you have a canonical set of coordinates there. Like, x, y, and z, and they're all perpendicular and everything, right? So that's kind of a coordinate representation of this to some extent. And it doesn't account for the potential of being on a curved space. So let me give you a more generalized definition, by the way, which will be exactly that, but in different notation. Okay? Turns out to be exactly that. And that is, this d2 of f should be the derivative of df. So, in fact, here, I like my equal signs to line up. And so, before I write down what this is exactly, I want d2f to equal the covariant derivative of df. I mean, now you're like, what do you mean exactly? Yeah, I want it to be, obviously the Hessian is like the derivative of the gradient, right? In some sense, right? And so this is where we want to make sense of this. So what I really want to make sense of, given a tensor t, so given a tensor t, define the covariant derivative of t. That sounds like a pretty good exercise for us to do, right? I mean, you should be able to take the derivative of a tensor. And so let's say you have some tensor t of x comma y. Let's say y comma z. And that's a tensor, okay? Now that is a 2 tensor. Why? I gave you an example of a 2 tensor because it has each 2 vector fields, gives you a real number back. Okay, so the metric is a 2 tensor. And now what I want to do is, I want to take the covariant derivative and the direction of a vector x of t. Okay? Now I'm only taking the derivative of t. Okay? Now what you get when you take a directional derivative, it's sort of like a directional derivative, but it's a covariant derivative. Okay? Now we haven't defined this yet. I'm about to define it. Okay? Because we know how to take the covariant derivative of vector fields, but we don't know how to take the covariant derivative of tensors yet. So we have to define that. Like this word covariant, again, doesn't really mean anything, right? It's just saying we're doing something more interesting than a directional derivative, right? We're doing, covariant derivative of vector fields, this thing. Covariant derivative of a tensor, I'm about to tell you what it is. But of course, it's going to be the same way that the covariant derivative of a vector field is a vector field. The covariant derivative of a tensor is, again, a tensor. So this thing also eats 2 vector fields, y and z. Okay? I'm going to give you the definition of what this is. Okay? Now you'd be tempted to say, maybe what we should do is we have t of y, z, and then we could, and that's a function, isn't it, right? And then what we could do is just take the directional derivative of that function. So that would be a tempting thing to do. At least gives you a number out. I mean, what is, I need a number here, right? This is, when you plug in y and z to this 2 tensors, you're supposed to get a number out. Give me a number. Okay, well, I could do that. That's a number. It's a real number at each point. But then if you look at this, you're like, but wait a second, doesn't this depend on y and z? It seems like this depends on the derivatives of y and z, not just the values of y and z. And in fact, it does. And it turns out this is not even a tensor. So the fact that we're trying to come up with a definition here, right? The point is, even if t is defined to be a tensor, this is not a tensor. Why? Because if I multiply y by a function f, I replace y with fy, that f will factor out here, but then you'll get derivatives of f here. You guys see that? So this is not this is not a tensor, And so what you have to do is say, well, I don't want those derivatives to show up. So what I'm going to do is I'm going to do a little bit. Well, I like the product rule. You guys like the product rule? Yeah. So I realize this has derivatives of y and z in there. So I'm like, you know what? Subtract off those derivatives. So minus t of, and then take the derivative in the direction of x of y, and then minus t of y, covariant derivative of z in the direction of x as well. Okay, and I hope this seems reasonably natural to you. What I'm basically saying is, look, to get the derivative of t, I'm taking the total derivative of t, y, and z, and then subtracting off the derivatives, the contribution of the derivative of y and the contribution of the derivative of z. Okay? Plausible, but here's the key point. This right here, this definition is a tensor. So we're going to use it. Okay? Proof. Proof. Okay, so let's put a box around this, right? This is the definition of the derivative of a tensor. We'll go ahead and. So let's be clear. we'll also write this, by the way, this is notation first of all. So the derivative of a tensor, of a 2 tensor, the covariant derivative of a 2 tensor is a 3 tensor in the sense that if we think of this x, the direction that you're taking the derivative of with respect as another slot, right? And so that's, and the claim is that this is multilinear, or trilinear in this case, right? Now it's obviously linear in the x slot. Can you all see that? If I were to take x and multiply it, replace x with f times x, the f is just right there. It factors out here. T is assumed to be multilinear, so it factors out. And the same here, everything just factors out. So clearly, this thing is multilinear in the x slot. Okay? And the proof for the y and the z slots are the same, so we just do the y slot. Okay? And that is, if you look at what is this. Well, I'll use this notation here. Okay, just plug into the formula, right? So you see, wherever you see a y, you put an fy. You guys better check me here. No? I'm actually off my notes by quite a bit. But. Okay, so that's what you get. If I take this definition here, and then I just plug, wherever I see a y, put an fy, right? That y becomes an fy. That y becomes an fy, right? And then, notice what happens. By assumption, we're assuming that t is a tensor. We're assuming t is a tensor, so that f just factors out, right? Okay, here we've got to do the product rule, right? So we get x of f times y plus f x, y, z. And then here we're assuming that t is a tensor, so the f just factors out. Any questions about that first line? The t is a tensor, the f just factors out. I'm going to work with that in a second. Here I got to use the product rule, right? So I'm getting derivatives of f there. That's a bad term. That can't stick around. At the end of the day, it's going to have to cancel somehow. And that f here just factored out because t is assumed to be a tensor. And then you look at this, and you're like, oh, okay. So I'm going to get a derivative term here, which is x of f. How about this? Let me just look at the terms that don't have derivatives of f in them. Is that okay? Let's look at the term. Look at the terms that don't have derivatives of f. So when I do the product rule here, right, I'm going to get f times the total derivative of x of this, which is that right here, right? And then I'm going to get minus, ignore this term here. I'm going to use the distributive law on this term, the linearity. I'm going to get minus, and then I'm going to have this f factors out here, right? So I'm going to get f times this, and then I already have f times that, right? So the first thing, the terms that don't have any derivatives of f is just going to be f of times all of this, right? Which is t of x, y, z. Plus the derivative terms. Does everybody agree with that? In other words, another way to think of it is, imagine f was just a constant like 5, right? Then actually the 5 does just factor out, right? It's only, this is the derivatives of f that we need to keep track of. So, okay, now where are all the derivative terms? Well, we've got this term here. We're going to have an x of f times ty of yz. And then there's only one other derivative f term. It's this one right here, right? And then you say minus, and I can just, that's a function in front of the yt is, I'm using the distributive law here, right? So I get an x of f t of y comma z. and you look at that, wait a second, this term is the same as that term. So it cancels, and therefore we have, that cancels with that, and so we have our linearity. It is in fact linear in the second slot. Same proof for the third slot. It's basically the same proof. Yes?
Why can we reslot so that last line we're putting the x back in like to the tensor? Why can you do that?
Where?
To the left, the bot. Yes.
Okay. I skipped a step. My apologies. Okay. I'm really taxing you guys here. What I said, these terms here is a collection of a bunch of terms, okay? So when I write t of x, y, z, what I mean is this whole thing here, okay? And what I'm pointing out is that, and see those three terms here? Well, there's three terms here that just have f's, no derivatives of s. For example, if I take this x and I'm doing the product rule, there's two terms, right? The second term is f times the x derivative of this. That's that.
Okay.
All right.
Gotcha.
And then here I have f. If I do the distributive law here, I have t of f of this comma z. When the f factors out, I get that term. And then over here, the same thing. The f is already factored out. It's f times that term. Okay. Good question. Other questions? So what all this was for was to prove to you that this is the only reasonable. In fact, this is what the covariant derivative of a tensor is. All right. There is no other competition for what the definition should or could be. Because this is, in fact, it's a tensor, right? And not only that, then you get a product rule. Isn't that nice? It's like the definition gives you the product rule. It's saying, if you take these negative terms and put them to the other side, it's saying, look, whenever you have a tensor, the total derivative in the direction of x is, in fact, the derivative of t, comma, y, z, and then plus these other derivatives. So you get a product rule in the definition. You guys see the point? So it's like, oh, okay, we'll do that. Okay? So that's a definition. Definition. And the key point is that given a tensor, you get a tensor. You take a covariant derivative of a tensor, you get another tensor. Well, but tensors are amazing things. They have these amazing properties about being multilinear. Fair enough? Okay, great. Now I can tell you what the Hessian is. Because the Hessian is just the covariant derivative of the differential of the function, df. Okay? And so we just want this to be the covariant derivative and the direction of y of df of z. You guys see what I did there? I have some tensor df. We already defined it. It's just directional derivatives. And I want to take its covariant derivative in the direction of y, and then z is, the thing you put into df. And so you say, okay, well, what is that? Well, it's the total derivative. It's y of df of z minus df, and you can take the derivative of z. You guys, so almost like that's the definition, but I want y'all to recognize, at some point you start to get used to this. What you realize is, okay, I want a two tensor. I want to take the derivative of df, so I'll do the total derivative, but then I got to subtract off the contribution due to the fact that z is changing. Really, I want the derivative of df. I don't want to take the derivative of z, so that's why I got to subtract it off. You guys get the idea? So this actually kind of makes sense. And then you just follow this definition, and you say, well, what's df of z? Well, df of z is the thing above there, right? So then what we have is y of z of f minus, and then we have df of this, and so that just means take the covariant derivative of z in the direction of y, and then take the directional derivative of f in that direction. And there you go. That's what the Hessian of f is. Okay? And the way to think of it is, well, it's sort of two derivatives. It's a derivative in z and then the derivative in y, right? But then the problem is this is capturing derivatives of z's. I want the second derivative of f. I don't want derivatives of z in there, right? And so you say, well, subtract off the contribution due to the derivatives of z. You guys get the idea? And so now this is, in fact, bilinear. It's linear in the y slot and linear in the z slot. Yes?
Could you flip the order?
Great question.
Okay.
Because what you're saying is, I remember my multivariable. You remember your multivariable calculus saying it's symmetric in y and z, right? Guess what? This is too. If you switch these two, guess what? Over here you get the definition of the Lie bracket of y and z, and over here you get the torsion term, right? And so remember, we're assuming that's 0. Okay, so if I take this and compare it to this, right? I'm gonna erase this in just a second, right? So, I'll say, what about, just flip the y and the y and the z, right? And then what my claim is to give you the same answer. Why? Because I'll subtract the 2, okay? When you subtract the 2, you get y. What is the difference of 2? This is just the Lie bracket. Would you guys agree? This is the Lie bracket applied to f. Right? This minus that is the definition of the Lie bracket. It's the vector field, right? That is the difference of those second derivatives, whatever that vector field is. And then over here you have minus but then wait a second, that equals that. That's our zero torsion assumption about, remember we had 2 properties that we defined the Levi-Civita connection with that came up with the causal formula, and was that the Lie bracket equals this torsion term. Okay, and we said that these are equal, so this difference equals 0. 0 applied to f, which is 0. So in fact, that zero torsion assumption in our connection gives us that this thing is symmetric. Okay, I'm gonna erase this for board space. Questions? If you have any questions about that, yes.
Actually, this is kind of unrelated, but is a 2 tensor the same thing as saying a rank 2 tensor?
I think that terminology is sometimes used. Yeah. There's show me the context, because rank can mean a lot of different things in a lot of different contexts. But really, there's two. I'm simplifying the discussion right now, because there's also this is actually a 0-4 tensor. And then you say, well, what's a 0-4 tensor? What's a 4-0 tensor? Sometimes it's a 1-3 tensor. And I'm simplifying the discussion right now. So let me not get off on that tangent right this second. Right now, we're only plugging in vector fields to our tensors. And so I'll just call that a 4 tensor. And morally, this has got all the interesting aspects. Turns out you can turn in covector fields. You can have, instead of putting vector fields into your tensors, you can put covector fields in there as well. Doesn't actually give you a whole lot more, but it's a nice thing to understand. Turns out, and but we haven't had that discussion yet, so let me just postpone it. Okay, so by the way, what the thing I just erased demonstrates is that this 2 tensor is symmetric. I'm going to go ahead and erase this too. Keep this definition on the board. Okay, so happens, PS D2F is symmetric. So that means is if you put in y or z or 0y, it doesn't matter the order, you get the same answer. Okay? And by the way, that's what you remember from your understanding of the Hessian. Okay, so a 3 tensor. Or should we just stop at 2 tensors? Is that enough? We've gone up to 2 tensors. Maybe that's enough. Okay. What do you think? I mean, no one really needs to go beyond 2 tensors, do they? What do y'all think? Should we keep on going? Yes.
Question about the definition.
Yep.
If you have a bilinear thing in like R2 or whatever, and you take the derivative of that, it usually is not bilinear, the outcome. Why are we keeping the derivative of a tensor still like multilinear or whatever in higher dimensions by adding the terms in the...
Yeah, so the
like
summary...
What is like conceptually important about it?
The point is it's a magic definition.
Okay.
What's magic about it is that it's a definition that you give me a tensor T and its covariant derivative will also be a tensor.
It will, as in it conceptually will, or mathematically we made it that
It's a
way?
theorem we just proved. I just erased the proof.
Cool.
All right. But what I erased was the proof that this, in fact, is trilinear. It's linear in the x, y, and z slots.
But we proved a definition.
We define the covariant derivative of the tensor to be this, and then we prove that it, in fact, is a tensor. So by definition,
So does the definition come first or tensor
definition.
come first? Okay,
Definition comes
cool.
first, then we prove it's a tensor.
Cool.
So technically, this is just a covariant derivative of t. Then we prove it's a tensor. Then we call it the, and then we say, by the way, the covariant derivative of a tensor is a tensor.
Cool.
Okay. Good questions. Other questions? Yes.
I don't know if this is along the same lines, but like, why do we want the derivative to be a tensor?
Because anything that's not a tensor is so unimaginably complicated, we don't even want to think about it. So you think this is complicated, right? Point is, how about this? The next revolution in differential geometry will be when people are willing to consider things more complicated than tensors, right? Tensors, okay, they seem complicated, but in fact they are the simplest things. That's the whole reason we want tensors, is because we don't even want to think about anything. We want the simplest things we could possibly deal with. And being multilinear, linear in each slot, right? It's like, oh, okay, that's such a nice property. Let's keep that for as long as we can. And let's understand all these multilinear things first before we even consider anything else. Does that make sense? Because I mean, clearly, that's huge, right? I mean, it's like, oh, multilinear. That's going to keep things simple. And let me just give you all another example of why that's nice. Is that you all know that the 2 tensor, in the case of this Hessian, you all know it's a matrix, right? So you're like, come on, why are you writing it this way? Why don't you just tell us what the matrix is, right? Okay. So, here's your manifold. There's your point P. There's your tangent plane, right? And then imagine you have basis vectors. Now we called them XU and XV in class, right? But now let's just call them partial 1 and partial 2 up to n. So we'll say partial 1, partial 2, comma, all the way up to partial n. These are a basis vectors for the tangent plane at the point P. Okay, so we'll call this manifold M. The point P, tangent plane is that plane drawn. We use x, u, and xv as basis vectors for that tangent plane before. Now we'll use partial 1, partial 2 up to partial n. Fair enough? And then if you do that, any vector field x is just going to be xi partial I, for example, right? Summation implied. I got a raised I and a lowered I, right? So it's x1 partial 1, x2 partial 2 plus x3 partial 3. I think I left out a plus. x1 partial 1 plus x2 partial 2. Everybody agree? It's like saying, instead of saying the vector 3, 4, 5, we're saying 3i plus 4j plus 5k. Fair enough? Okay. And we could do the same thing for another vector field y, for example. Y equals yj partial j. And z and so on, right? And so then what is t of x comma y equal? Well, t of x comma y is a tensor. And so you just plug that in. It's t of xi partial I, comma y, j partial j. Summation's implied. Fair enough. By the way, we have n squared terms there. I goes from 1 to n. J goes from 1 to n. I didn't write down a single summation sign, but actually it's implied, right? Now, where is the summation sign? Well, it's inside. It's inside the t, right? But here's the beautiful thing. And it's outside. Wherever you want to put it, I don't care. It's linear, right? Isn't that nice? I mean, so I might as well just take the summation outside, actually. It doesn't matter where you put the summation sign, because t is linear. Okay? That's why, I mean, everything Einstein ever did was with tensors, and it's linear. It doesn't matter where you put the summation sign. Einstein's summation notation wouldn't even work if we weren't talking about tensors. Okay. And then you can also factor these xi's out. So what you get then is xi yj times t of partial I partial j. And so all you actually need to know are those n squared numbers. Those n squared numbers is the matrix, right? So this thing right there we can call Tij. So the point is that if you know what T is on T of partial I partial j is, then you know that Tij, call that Tij. That's a matrix. I goes from 1 to n, j goes from 1 to n. You get a matrix of numbers that has the equivalent information to understanding what this tensor is, because give me any x and y, you just tell me what the xi and yj's are, and just plug into this formula, sum over the n squared terms, and you get the answer. By the way, this is sort of like an n by n matrix. That's a 1 by n. That's an n by 1. It's the whole thing you learned from multivariable calculus, right? But guess what? It's not just true for two tensors. It's true for any number, any degree tensor. So I could have t of x comma y comma z, and I would just have x I y j z upper k t I j k. You guys get the idea? And so this is why we love tensors, is because it just means. And by the way, physicists won't even write down the tensor t. They'll say Tij. And they'll just talk about that as the tensor, because it has all the information anyway. And there's actually something rather efficient about what they're doing. Okay?
Us mechanical engineers really like tensors. We do that too. Like stress strain.
Awesome.
Moments of inertia, it's all tensors.
Sort of, you are on the physicist side of things, probably.
Yeah.
You're at TIJs and stuff like that, yeah.
Mhm.
Cool. No, and actually, even as a mathematician, I like it too, because that tells you it's a two tensor. Right? Tij, like, oh, it's a two tensor. Right? Or whereas if I just write down T, everyone's wondering, like, well, what kind of tensor is it, right? Is it two tensor, three tensor? Okay. Okay, so let me give you an example of a three tensor. Now, this is, yes, go ahead.
So the Hessian is a matrix.
It is, well, it's a all matter of definitions and stuff and vocabulary and all that kind of stuff. The point is that the information of the Hessian D2F is in one-to-one correspondence with, if you have a basis, with the Tij. If you have this Tij, it tells you exactly what T is, right? So T of x comma y just equals that. So really, this has all the information you need. So yeah, in that sense, yeah, the Hessian is a matrix. It's a n by n matrix. Guess what? Df is like the gradient. It's a 1 by n matrix, right? And same reason, right? When you work this out, it's z upper I, f lower I, where f lower I is the partial derivative of f. And so, anybody want to propose a three tensor? Because now this is a four tensor. You might want to propose a three tensor. By the way, there aren't that many three tensors. I mean, there are, but I mean, I'll tell you one we could do, and it's not discussed much. And by the way, my presentation up to this point is pretty standard. Now I'm going to do something that I never saw in a class. This was my idea. Is why don't we just, I mean, it's not, of course it exists. Everybody knows this on some level, but I don't see it. It's not usually presented in textbooks. Why don't we just look at the third derivative of f? I mean, we did the first derivative, we did the second derivative. The first derivative was trivial. Second derivative, not trivial. Right? This Hessian thing's already kind of interesting, right? It's symmetric at least. That came from the zero torsion property, but I'm going to say this is not trivial. So let's do the third derivative. What is d3 of f? And then frankly, we should do d4 and then d5 and just keep on going until we can't stand it no more, right? I mean, if there's one lesson I learned from geometry, it's just you never stop. You just keep on going until you're absolutely certain nothing interesting is going to happen beyond that. Turns out something really fascinating happens when you look at the third derivative of f. Something fascinating. Something that's qualitatively different than the second derivative. And so let me show you what it is. All right. Well, first of all, we use the formula. By the way, what I'm about to show you is not intuitive to me at all. Okay? I really should teach my 8-year-old this stuff. And so that by the time he's my age, maybe this would be intuitive to him. Right? I think that's true, by the way. If you brainwash your kids when they're young. I think I've done this a little bit. Because I used to teach them all kinds of stuff when they're young, like math, this or that, and everything. And then I'll try to explain it to them again like 5 years later, and they'll look at me like, do you think I'm dumb? You know? It's like, why are you insulting me? right? And it's like they think it's just obvious to them, but then I know, nope, I pre-programmed you. So do that with your kids someday. It's interesting. They internalize it. Like I almost feel bad about it. That's like you're like a little mind, right? And you control it so much, right?
As long as you're aware.
Yeah. I think I've only programmed them with good things, as far as I know. But that's the problem. It's the things you're not aware of. That's what gets you, right? Okay. So what we're going to do is we're going to take the covariant derivative in the x direction of d2f, right? Of yz, right? That's what we're going to do. Okay. Gets a little messy. Okay, now what is this going to equal? We're, by the way, outside of realm of intuition now for any normal person, right? And now we're just doing the algebra. Okay, well, I guess it's the total derivative. You take d2 of f, d2f, you take the total derivative of this, right? And then you guys subtract off the contribution from y and z, right? So you say minus d2f of the y derivative, and then minus the contribution of the z derivative. Oops. Is that right? You guys agree with that? Now, again, you have to do that if you want this to be a tensor. All right, we're using this definition of tensor here. You take the total derivative of the thing you had before, and then subtract off the contributions due to y and z. That's what we did. Which equals? I have to come over here if you guys don't mind. Okay, we need some space. What is this? This, I got a formula for it. It's right there, right? So it's x of, and then just copy in this stuff, right? I think that board work right here. I'm going to go ahead and distribute this, right? So it's x of this. So the first term is going to be x of y of z of f, right? And then minus x of that. Fair enough? And then I have to subtract off minus d2f of this. So now what I do is I come back here, and wherever you see a y, you put the derivative of y there, okay, or in the direction of x. Okay. I do it right?
Plus.
Plus. Thank you. Yeah, so save the day. Thank you. Minus, so we'll just check that. We did minus this, but wherever you see, first of all, it's a minus, so it comes a minus and a plus. And wherever you see a y, you put the derivative of y. And then we do the same thing here, but wherever you see a z, put in the derivative of z. Okay? So, and then subtracting it off. So, minus y the plus sign this time. Okay, wherever you saw a z, you put in the derivative of z. We okay? Trying to understand what I meant when I wrote something down now. Let's just see here. X, Y, Z. I circled some terms here. Okay. And there you go. That's what it is. We have a 3 tensor. Believe it or not, that's a 3 tensor. Okay? You believe it's a 3 tensor? Now keep in mind, if I change a minus to a plus or mess with this at all, it's not going to be a tensor at all, right? This is something amazing, right? I mean, that looks ridiculous. In other words, if I take, this is a 3 tensor, meaning that if I replace z by, let's say, well, I don't want to use f because I have f used already, but let's say I take z and I multiply it by a function h, right? So I replace z with h times z. There will be an h times z there. I'm going to get 2 derivatives of that h, right? But I'm also going to get 2 derivatives of the h there, right? And I'm going to get a first derivative there, and a first derivative there, first derivative here, and 2 more derivatives there. And guess what? All the first and second derivatives of h are just going to miraculously cancel. That's going to be a tensor. Why? Because I gave it a tensor, and so what comes out is a tensor. So now I have a 3 tensor. Okay, now. Kind of messy, isn't it?
A little bit.
Yes.
So I understand in the 2 tensor why we're subtracting out like the extra derivatives of f, but in the 3 tensor we're doing that, but we're also adding some terms back. Is that because when we're going through with that subtraction, we're getting rid of like some of the z derivatives? Or-
Yeah, it's all there. Look, it's a magic formula, right?
Okay.
Like at this point, I encourage you to try and make intuitive sense out of it, but it's just a formula.
Okay, all right. Yeah,
Like,
that's what I was trying to do.
It really is. I mean, you're welcome to try, okay? But like, you know, you'd be going beyond what I'm doing right now if you do that. It's just a formula. Now, but theorem. Is it symmetric? Right? Well, guess what? It has some symmetry. D3f of x comma, let's switch the last two, z and y. That is symmetric there. Okay, so when you're doing, it's symmetric in the last two. Okay, here. Symmetric in the last two. And you can look at this formula and see why, but really it just comes from the fact that it was already symmetric. I mean, the 2 tensor was symmetric in y and z, right? So theorem, the 2 tensor, d2f, right, of yz is equal to d2f of zy. Okay, so the fact that the 2 tensor is symmetric is in y and z is why the 3 tensor is symmetric in y and z. Okay. That raises the question, well, how about in x and y? Is it symmetric in x and y? Okay. The answer is no. It's not symmetric in x and y. And so then, and not, it doesn't have to be anyway. So the point is that, in fact, then the question becomes, what is, so if you're like, okay, well, what is it then? What if I look at D3 of f of, all my notes here. of yx z minus d3f of xyz. Now, if it was 0, then that would be symmetric. So what we're doing is we're looking at switching the y and the x here, right? If that equals 0, that would be the statement that D3 is symmetric with switching it for the first two. By the way, switching the first and the third is achieved by some combination of switching the last two and the first two, right? So if we can understand what happens when you switch the first two, we already know what happens, nothing happens when you switch the last two, right? Then we understand about all switches, okay? So this is all the only thing, we need a formula for this. And I think you can see that it's going to be a bit complicated, right? I'm going to take this formula here for x, y, and z, right? That's that. And then that's why I'm subtracting. And then what you start with is this here, but it's where you see a y and an x switching. Okay? And turns out that's what the Riemann curvature tensor is. That's the Riemann curvature tensor. Okay. Now, you see a bunch of these terms. Oh, it does kind of look similar. How do we see that exactly? Let me show you. Okay, it's this thing here, right? Remember, I started the class by saying, "Wow, it's a magical formula." Now I'm showing you where it comes from. It's actually forced upon you. If you even muster up the courage to ask, "What's the third derivative of a function?" you cannot avoid the Riemann curvature tensor. Okay, and that's all of the curvature quantities on a manifold. And by the way, you could go up to the fourth derivative, fifth derivative, sixth derivative. It turns out nothing new or interesting particularly happens. I mean, the SR is going to be a little bit interesting. Actually, probably overstating it a bit, but I'm going to say you might be able to get some identities for the Riemann curvature tensor or something like that. But the point is that the Riemann curvature tensor is all of the curvature. There is no more curvature to understand. So it's all about understanding the Riemann curvature tensor after that. Now, how do you prove this? All right. Well, let's just look at it. D3, this y x z minus D3 f x y z. Now it's a mess of algebra we're going to be doing here, right? A mess of algebra, right? Look at this and then subtract it from itself, right? What do you get? Let's see if I can write this down. And of course, it's exactly the negative of what I have in my notes. But anyway, okay. So it's y. So the first term is, we can kind of do each term at a time. So switch, what is this? You take that, but you got to switch the x and the y, right? Because that was x, y, z, and this is y, x, z. Okay, so we switch the x and the y. I get y, x, z of f. Okay, now what was the first term from that? That was just in the normal order. X, y, z, f. Okay? And then I need a lot of space. I'm going to have to come over here, right? This is adding on to the right-hand side here. And then plus, okay, now I remember why I had these two terms circled. Here, let's see here. You guys see these two terms right here? What I want you to see is that these terms are the same except you switch x and y, right? That x becomes a y, that y becomes an x. So therefore, when I symmetrize, when I symmetrize on the x and the y, or anti-symmetrize on the x and the y, right? Those terms have to go away, right? Because when I switch the x to the y, this becomes that becomes that, so the difference is 0. You guys see that? When I switch x and y, that term becomes that term. When I switch x and y, that term becomes that term. And then when I subtract them, in other words, this minus that cancels. Okay? So that's nice. So now let's come to the next term here. And so then what we have is we got to switch the x and the y there. So the first term is switch the x and the y. And then we're subtracting off the way it was originally. And then apply that to z of f. Okay, so now we got that term. So we got that one for both, we got that one for both, those canceled. Okay, so then we have let's go to this term now, the last one, and then we'll do this one last, okay? And so then we have plus, no, let's do this one now. Plus, let me follow my notes. Okay, so we'll do this one next. And so we got the first term is we have switch the x and the y, right? So plus no, okay. By the way, I think this is minus. Z. If you guys don't mind, I'll collect some terms here. This is all applied to F here, okay? So, and then minus when you subtract this, when you minus, just leave it like that. And then this term here, look what we get. We actually get a Lie bracket term. Do y'all remember the identity for the Lie bracket, right? That the bracket of x and y equals the covariant derivative of y in the direction of x minus the covariant derivative of x in the direction of y, right? Okay, so when I anti-symmetrize this term here, I just get a Lie bracket term. And so I just get plus the covariant derivative Lie bracket of y and x here, applied to z. And then look at this, guys. Y'all see yx minus xy, that's a Lie bracket. That's the Lie bracket, so what this equals then is the Lie bracket of y and x. That's a vector field. And then apply that to z of f. Okay, that's what this is, right? Because we have a function here, the function is z of f, z applied to f. But then we have the Lie bracket there. But wait a second, this, by the Lie bracket identity, that's the same thing, except y, x, did I get off by a sign somehow? Y, x, yeah.
The initial term was negative.
Where? Did I modify a sign here?
I think that.
Is this minus?
Yeah, that should be minus.
It is? Okay. We take your word for it. I think it gets me good right. If it does, okay.
Because you took it from the
Thank you. Thank you. Okay, so then this is then minus a Lie bracket y and x applied to zf. Those two terms cancel, right? And so that cancels with this. So what you're left with is just that, but that in fact is your Riemann curvature tensor. But the one thing I left off is what is the definition of the gradient of f? Well, the gradient of f is defined to be whenever you have a vector field applied to f, that's defined to be the dot product of that vector field with gradient f. Okay, so this is the definition here of what the gradient of f is. So you see we have this vector field applied to f. What is the vector field? The vector field is in fact this whole thing is underlined. And so then you have to dot product with grad f, and if you look at that, that's in fact the definition of the Riemann curvature tensor that I wrote. Okay. So what's the bottom line? The bottom line is that we can't use our intuition of anymore, right? We're not thinking, it's not a surface in R3 anymore. Thank God we started with that, because by the way, I'm still always thinking of a surface in R3. But I had to, here, there wasn't a lot of pictures I drew, right? It's all a bunch of calculations. We like tensors because they're simple, right? We're just trying to keep life simple for us. And if there's something I really want you to learn today is, first of all, what a tensor is, something that's multilinear. You now see what the Riemann curvature tensor is. It's this complicated formula. It's natural. Why? Because, I mean, third derivatives of functions. Come on, I mean, if you don't know how to take a third derivative, what are we doing here, right? Right? And it shows up in the, so it shows up. So we realize that this tensor is forced upon you. And then it turns out this is all of curvature, okay? And so what we'll do next time is we'll talk about, okay, so what is this? It's a generalization of the Gauss curvature. But it's not one number at each point. It's n to the fourth numbers, right? That's the point, is that there's a 4 tensor. And so this is, in other words, if we look at the Riemann curvature tensor, partial I, partial J, partial K, partial L, and we call that R, I, J, K, L, and I, J, K, and L all go from 1 to n. At n to the fourth numbers is the Riemann curvature tensor. Now, I'll just end on this. And if you're in dimension n, how many components does the Riemann curvature tensor actually have? Well, in principle, it should be n to the fourth, right? So if you're in dimension 2, in principle, we've come up with 16 numbers, right? But guess what? They're all either 0, the Gauss curvature, or the negative of the Gauss curvature. Turns out the Riemann curvature tensor has symmetries. Just like the Hessian, the Hessian was symmetric. Turns out the Riemann curvature tensor has symmetries. You can see one of them really easily. It's anti-symmetric in x and w and x here. The first 2 slots, if I switch them, it's going to be anti-symmetric. Turns out it's anti-symmetric in the first 2. It's also anti-symmetric in the second 2. If you replace the first 2 as a pair with the last 2 as a pair, just swap them like that, symmetric. And there's also a cyclic sum that adds up to 0 in the first 3. So when you add up all the symmetries, the actual number of components is n squared times n squared minus 1 divided by 12. And so in dimension 2, you'll see that's 4 times 3 over 12, which is 1. That's the Gauss curvature. And in dimension 3, you'll see that's 9 times 8, 72 over 12, which is 6. And in dimension 4, 16 times 15, which is 240 divided by 12, which is 20. And so that's how, and it goes up from there. It goes up like into the fourth over 12, right? So now you can see why curvature gets more complicated as you go higher dimensions, because Gauss curvature is one number to keep track of. In 3 dimensions, you've already got 6 numbers to keep track of. And in the space-time, which is the Big Bang and general relativity and all that, you got 20 numbers to keep track of. And guess what? When we wrote G equal 8 pi t, the Einstein curvature tensor, that G is a symmetric 4 by 4 matrix, so it looks like 16 numbers, but it's symmetric, so it's actually only 10. And that's half of the Riemann curvature tensor. And so half the curvature you're setting equal to the matter density. And the other half of the curvature tensor, called the Weil curvature tensor, which we'll talk about later, is not determined by the matter density. And so that's the kind of the contradiction, right? It's like matter equal, matter curves space-time. Yeah, well, it curves the Einstein curvature tensor. But there are other, but that curvature can propagate, and it's propagating in the other 10, the Weil curvature. And so, like, what is the gravitational field? Because the curvature isn't just locally, isn't just where the matter is. The space then has a dimple that radiates out, right? And that's in the Weil curvature tensor. So, so you can see why it's studying space-times are really quite interesting, because you have 20 Gauss curvatures to keep track of at each point. So it's like 20 functions, not one function. Okay, if you guys enjoyed, we'll get into the Einstein curvature tensor and study Riemann curvature tensor some more next time. But remember what tensors are, and remember what the Riemann curvature tensor is.